Welcome to section 4 of the Mastering Keras course. This is a section on advanced CNNs, and in particular a variety of layers and architectures that are of special use in advanced CNNs in recent times. So we're going to start off by looking at the Inception architecture, and this is named after a meme from the Inception movie that we have to go deeper. So Inception layers are an important addition to deep learning, and in particular to image analysis with deep learning. What Inception layers do is they permit parallel processing of inputs at different scales, and we'll look into this in more detail. They also allow the reduction in parameters so that we can work with deeper networks with the same sort of statistical complexity cost. And the famous example of Inception Networks is GoogleNet. So what we're going to be doing is we're going to look at the ideas behind Inception layers and Inception networks. In our Jupyter notebooks, we'll code basic and standard Inception blocks, and we'll just create some quick Inception networks utilizing these blocks that we code just so we can view the architecture. So we're not going to be solving a problem like we have with some of the other networks, with all of the other networks that we've looked at up to this point. And the reason for that is because really the Inception idea is a layer-based idea rather than a network-based idea. So we want to just see how we can build these Inception blocks, these Inception layers, and have a look at the resulting architecture rather than, as it were, looking at a whole new network form that we would try out on a toy problem. So a basic Inception block contains parallel convolutional layers with different size filters, and the examples we'll be looking at are 1x1, 3x3, and 5x5. This will make more sense when we look at the graphs. These are pretty common choices, but of course you could choose anything. In addition to these parallel convolutional layers, there's also a parallel max pooling layer. So we have 4 different layers inside the basic Inception block, each doing whatever they're doing: a 1x1 convolution, a 3x3 convolution, a 5x5 convolution, or a 3x3 max pooling. The results of these 4 different layers are then concatenated. And what this allows the model to do is to learn parallel filters of different, or potentially the same, size. And so it allows the Inception block as a whole to learn at multiple scales. And here's an example of a computational graph, a network graph, that incorporates 2 basic Inception layers. You can see here's our input layer, and we now have 3 convolutional layers, 1, 2, 3, and 1 max pooling layer. Then we have a concatenation of these 4 outputs from those 4 parallel operations, and that is the output of, as it were, the Inception block, which is then fed into the second Inception block, and once again we have 3 parallel convolutions going on and 1 parallel max pooling, and once again these 4 outputs are concatenated. Now, basic Inception blocks are well and good. They can, though, result in too many parameters. And remember, using too many parameters is dangerous because it results in higher statistical complexity and so increases the risk of overfitting. And of course, there's also a practical cost in the sense that it will require increased computational effort and therefore increased training time if you've got more parameters. So the standard Inception block actually adds another component to what we've just looked at, and this is to use 1x1 filters, 1x1 convolutions, to merge input into the Inception block for the more computationally costly convolutions inside the block. So the standard Inception block will have 3 parallel convolutions and 1 max pooling layer, but before the more complex filters, say the 3x3 and the 5x5, we'll have a 1x1 filter layer, a 1x1 convolution layer. And what that's going to do is it's going to merge together the input channels into a lower number of channels before passing it on to the more complex convolutions. It's also very common to have a 1x1 filter layer after the max pooling layer. For exactly the same reason, it can merge down the number of channels coming out of the max pooling layer, therefore reducing the number of channels that are going to be concatenated at the final step of the Inception block. And in this way, we reduce the number of parameters, reduce the complexity of the model we're working with. And here is the computational graph or network graph of a standard Inception, or 2 standard Inception blocks. So we see we've got the input layer up the top. We then have out on the right, we've got 1 convolution all on its own, and that's the 1x1 convolution. This is, remember, having a 1x1, a 3x3, and a 5x5. Well, the one-by-one convolution has no need for a preceding one-by-one convolution. It is not a complex convolution, and indeed it is itself a one-by-one convolution. So it's just on its own. We've got two convolutions over on the left. And before we do the complex convolutions, the 3x3 and the 5x5, we have before them some one-by-one convolutions that will merge together the input channels into a smaller number of channels before the complex convolution. And of course, the parameters of this one-by-one convolution are being learnt as we train the network, so it will learn how to merge the input channels together in ways that are useful for the more complex convolution to extract informative features. And likewise, the max pooling layer has a one-by-one convolution after it that will merge together the output channels of the max pooling so that we can add fewer channels into the concatenation. After the concatenation, the same thing is repeated. There's two standard inception blocks here. We can actually go a little bit further, ensuring we keep things simple, we keep the number of parameters down. On our left, we see a basic 1-3-5 inception block, so working with the 1x1, 3x3, and 5x5 convolution. This is basic, not in the sense of basic before, but it's standard as we just looked at, as we just thought about. So we've got the 1x1 convolution layers going in before the more complex convolutions. We've got a 1x1 convolution layer coming out after the max pooling. Now, it's possible to factorize down the more complex convolutions. One way of factorizing, say, a 5x5 convolution is to perform two 3x3 convolutions. And that's what we have in the second picture there. You can also start factorizing things into 1/n convolutions. And we can do these 1/n convolutions in parallel. And so over here on the right-hand side, we have a parallel factorization. So our 5x5 convolution becomes a 3x3 convolution, followed by parallel 1x3 and 3x1 convolutions. And our 3x3 convolution becomes a parallel 1x3 and 3x1 convolution. Being able to parallelize this means that we can run them faster. Being able to factorize it means that we can do the same amount of work, or very close to, with a smaller number of parameters, and therefore keep down the statistical complexity of the model. Now we're going to look in our Jupyter Notebook at how to code, how to implement the basic inception block and the standard inception block. Then we'll make some networks that allow us to view the architecture. But you can also try to code some of these factorized blocks. That's a good exercise, and put them in network architecture and see that you're getting out the computational graphs that we're seeing in these pictures. So let's open up our Jupyter Notebooks now for the module on inception layers. So here we are. So we're going to look at how to create inception layers for use in advanced convolutional neural networks. We're going to implement functions to create the basic and standard inception blocks, and then we'll create some models to visually examine the inception architecture. Like I said, since we're really looking at layers here rather than full network architectures, we're not going to be trying to solve a toy problem in this module. We'll just see how to implement the blocks that constitute these inception layers or inception blocks, and we will create them inside a network so that we can visually view the architecture. So we import the required libraries. The first thing we're going to do is to create a function to allow us to produce a basic inception block easily. So we're going to allow the caller to specify the number of 1x1, 3x3, and 5x5 filters to use. Of course, there's a whole lot more that you could allow the caller to specify, giving them more freedom to specify the contents and the makeup of the internal layers. But what we're going to do is just set, say, activation to ReLU, the size of the different convolution filters, the padding, size of the max pooling, etc. We're going to set all this, we're going to hard code it, and all the caller of this function can do is specify the number of filters for the 1x1, 3x3, and 5x5 convolutions. Notice how we're passing a layer in and returning a layer out. So let's create a model that consists of two of these basic inception blocks so that we can get its summary and graph its architecture. We'll just run our function here. Here's our simple model. We create an input layer. We pass the input layer to this basic inception module function. What that's going to do is be the layer in. The layer in will be passed to the first convolution. The first convolution will be passed to the second to the third. So you can see we've got our input layer here. Then we're going to pass our input layer to the basic inception module function and specify the number of 1x1, 3x3, and 5x5 filters. The input layer is then going to be passed to each of the convolution layers as input, and also to the max pooling as input. See, layer in is being passed to each of them. And then we get the output of those four layers and we concatenate, and we pass that concatenation as our output here. The output, here named iBlock1, Inception Block 1, can then be passed as the input layer to the second basic Inception module. Same thing happens, the concatenated output. Then finally, just to finish off the network, we flatten it, add a dense layer, add a softmax output, and create our model. We can then summarize the model and have a look at the plot. Now, the summary is linear, and that's actually less useful, more confusing in the case where we've got parallel layers going on. So it's much more conducive to understanding to look at of the computational graph. And here you say the input layer going to 4 parallel layers, 3 convolutions, 1 max pooling, then all getting concatenated together. That's the first inception block. Then the same thing happens in the second inception block. Okay, so that's our basic inception block. Let's now create a wrapper function to create a standard inception block. This is going to be very similar. We're going to allow the caller to specify the number of 1x1, 3x3, and 5x5 filters to use, but we're also going to let them specify the number of 1x1 filters, 1x1 convolutions to place before the 3x3 and 5x5 filter layers and after the max pooling layer. So you see here, we want to know the number of 1x1 convolutions to do. We want to know the number of channels to input into the 3x3 convolution. And that's, of course, going to be the number of 1x1 convolutions we perform before the 3x3 convolution. And then we want to know the number of convolution filters to use in the 3x3 convolution. Same thing for the 5x5 convolution. How many channels should we allow input into the 5x5 convolution? And how many channels output should the 5x5 convolution have? And finally, the number of max pooling output. How many 1x1 filters are we going to apply after the max pooling? Once we've got this information, we can set up the standard inception module. And of course, again, we concatenate at the end. We can do the same thing as before, create a little network so we can view the summary and the network graph. Network graphs come out a little big by default, clearly in Jupyter Notebook, but nonetheless, well, they do when you've got lots of parallel layers going on. Here we have our input layer, and then like in the picture in the slides, we've got the 1x1 filters before the complex convolutions and after the max pooling, and the 1x1 simple convolution just occurs on its own. The 1x1 simple convolution occurs on its own. So that's it for the coding in this module, but like I said before, it's a good exercise to try to code little wrapper functions to produce the factorized inception blocks. That's a nice exercise. Okay, so that's the first of the advanced convolutional neural network topics that we're looking at, these inception layers.